Here we go again. This is Professor Grenfell's Math 12 statistics class. Continuing talking about hypothesis testing. Now we're looking at the difference between two means when we have dependent samples. Again, I described this last time as the mean of differences rather than the difference of means. And this is going to be applicable anytime we are wanting to make a direct comparison of quantities that are directly related or dependent upon one another. So the example that I gave last time was, with left feet and right feet. If, we wanted to say are people's right feet in general longer than their left foot. And so we have to actually take the difference between one single person's right foot length minus the left foot length. This is yet another example where we're going to be looking at the same sort of thing. So a random sample of 9 local banks. Okay, so we'll jot down n equals 9 at least. Shows that their deposits in billions of dollars 3 years ago and their deposits in billions of dollars today. At alpha equals 0.05, can it be concluded that the average in deposits for banks is greater today than it was 3 years ago? So here we're going to say alpha equals 0.05, n is equal to 9, and this is one where I'm going to go through and collect, we're given all of the raw data, and we're going to go through and do the entire procedure all the way through, all by hand. So let's begin that right here. All right, so before we go into the mechanics, the procedure for the hypothesis test itself, we're going to go about all of the computations that we're going to need to do behind the scenes, so to speak, in order to be able to compute our test statistic. So here's what we're going to do. I made a little chart here for our our first sample right here. This is the bank deposits in billions of dollars from 3 years ago. That's this first column here. Then we have our second sample is the bank deposits current, okay, from the exact same banks. The banks are not the sample. The two different samples that we have are the figures from 3 years ago and the data, the numerical deposit values from today. Those are our two samples. The fact that we're looking at the same bank 3 years ago and then again today is what makes these two samples dependent, all right? Because they, the information 3 years ago and the information today, they're both coming from the same individual bank. So what we're going to do is we're going to jot down the data for 3 years ago. Their deposits, wrong color. Their deposits were 11.42, and these are in billions of dollars. So it's 11.42 billion. And for the current deposits, we have 16.69 billion. And then you'll notice I wrote these other two columns in the third column. We'll call this one column A. In the third column, we have D is defined as x1 minus x2. So here we're going to do 11.42 because that's what we're calling the x1. And we're subtracting away x2, that's the figure from today. So for this difference, for the first one, we get negative 5.27. And then in the last column, call this one column B, we're going to go ahead and just look at whatever we had in column A and square that result and write it down right here. So 5.27, whole thing squared, gives us 27.7729. And so we'll just go ahead and continue that same procedure, filling in all of the data that we have for all 9 of these banks. All right, so like I said, we had copied down all of the raw data. So in the first column, we put all of the figures from 3 years ago, and then in the second column, making sure to not switch up the banks. So these are still corresponding, this first set of figures, that's bank number 1, bank number 2, and so on and so forth. So we can't rearrange the order because these are dependent upon one another. We'll list all of this out, and then we're going to do, in this next row, 8.41 minus 9.44. That gives us a negative 1.03. Notice the way that we set up these subtractions, we're taking the figures from 3 years ago and subtracting what we have today. And so instead of thinking about it as a gain over the past 3 years, we're thinking of it as a drop the other way around. So if we reverse the order of the subtraction, we would see all positive figures. Now, this doesn't make a difference in terms of our test value and where it will be, but it does make a difference in terms of the type of hypothesis test, and whether it's a right-tailed test or a left-tailed test. All right, and then the next thing we have to do is take all of the values that we have here and go ahead and square them. And so for this next one, we get 1.0609 and so on and so forth. So we'll continue with that. And here we have all of the differences being computed. The first column minus the second column, so that's going to be column A. And then we just take those results and square them, and that's going here in column B. Now, I did mention we can't mix up the order. I did forget. I think it was supposed to be here, and this value or this bank's information got neglected, and so I did put that in at the end. But notice these two figures. That was the figure for bank. I believe it was bank 5 3 years ago, and there it is from today, the current. So as long as we don't mix up the data for the individual bank itself and confuse the banks with one another, as long as we don't do that, as long as we keep the banks paired together and keep these sample values that are dependent upon one another matched up together, then we'll be fine. We don't have to worry about that anymore. Then remember, totaling up column A, we'll just call this, for lack of a better term, I'll call it A. And this is going to be the summation of all of the D values. We'll sum up that whole first column, and we'll get negative 9.73. Okay? For the second column, we'll call this result, we'll call it B. Okay? And this is going to be the summation of the D squared values. And so what we get here is positive 40.5437. Right. So that is the bulk of the scratch work that we have to do. Now we got to go ahead and find our mean and the standard deviation for this distribution. So here we're going to flip back real quick. Column A, we're going to use this one. So yes, we had column A, and that represented the sum of the differences, so that's sigma of D, and that was 9.73, negative 9.73. So we had an average increase of $1.081 billion. And then we're going to go ahead and use B. I'm going to flip back and see what that was, 40.5437. Okay, and what was this? This was the summation of our D squareds. So where is this going to come in? We're going to use this when we calculate the standard deviation for this distribution. So we'll call that S, because it's from our sample. It's a sample standard deviation. And we'll say subscript, that's not a 0, that's a D. Let's make that a little bit nicer there. We're going to use the computation that is the shortcut. So we're not going to come back and look at this and then look at the actual differences and how they're compared to this. No, we're going to use this one where we go n times sigma of our d's, whole thing squared, minus the summation of d itself, and then we square that whole sum, and then divide by n times n minus 1. So that's why we wanted to do that scratch work ahead of time, because now the only things that are involved in this calculation are A and B, and then of course we have n equals 9 still. So we'll go ahead and substitute in everything in here properly and finish the calculation. So this gives us 9 in place of n. We have the sum of the d squares is 40.5437. Go ahead and put that in parentheses. We're going to subtract away the sum, which was negative 9.73. Okay, and after we add it all up, then we square that. So notice this one that we got from column A and this one that we got from column B, those are different. And so these two terms, this term and this term, better be different, right? You better not get 0 for the top. All right, and here we have n, let's go back, 9 in place of n times, well, no calculator, we'll just do 8, right? And then don't forget, we're going to take the square root of that whole thing. All right, so that's what we need to do. We'll pause to let the calculator catch up. And we get out 1.937. Right, so that is our standard deviation and the sample mean for our distribution of differences in these data values. Now, all of that was the scratch work. Now let's go into the easy part. The easy part is the hypothesis test itself, because there's 5 steps, same 5 steps every single time, no matter what the problem differences are. The format, the template that we use for doing a hypothesis test is the same every single time. So here, the claim, or sorry, not the claim, the null hypothesis is going to say, look, there's no difference, didn't change. The average of the differences is just 0, okay? And then notice we're taking the figures from 3 years ago minus what we got in the ledger today. And notice I wouldn't have done it like this. I just started out this way. But in reality, what will we do if we want to know how much our accounts, our deposits increased? We take the figures from today and subtract what they were in the past. So if we want to say, look, the difference, the increase is positive, and we did the subtraction in the opposite order, then that is actually saying that these differences here, the average of all of them, is going to be negative, okay? So we started out with some money 3 years ago. If it goes up, then those subtractions will be negative. And so that's what we are trying to assert here. We're trying to say that they have gone up. And so in that sense, when we do the ledgers from 3 years ago minus the ledgers from today, we should be seeing that we had more today, and so our subtraction is a negative value. All right, this one is a t-test. In 9.2 and 9.3, we're going to be using the t-distribution. So in step 2, we're going to find the critical values, but I always take this opportunity to go ahead and sketch the distribution curve. And since That one looks so much like the z distribution. I'm going to write right next to the graph df equals 8 because the z distribution doesn't have degrees of freedom. There is no df on the z distribution. So hopefully this will remind me that I better look at the t distribution. Now we have our significance level for our test. Alpha equals 0.05. So that means in this little sketch of the critical region, we have 0.025 on this side and 0.025 on this side. We don't need to do anything with that actual figure. We're just going to go to table F. Don't look at... Oh, I'm sorry. Hang on one second. Okay, just kidding about this because... oh yeah, I did it wrong. Let's just call it what it is. I goofed it up. That's not it. Okay, let's try it again. Here's our distribution curve. It's a bell-shaped curve, pretty much. Okay, we'll say df equals 8. That tells us that it's the t distribution. And what type of a test is this? It is a left-tailed test. So that means I should only look for one critical value, and our rejection region is just going to be the left tail shaded underneath. So all we're going to do here is put in our degrees of freedom, use the correct alpha that we have, alpha equals 0.05, and then make sure that we're thinking about the right type of test. Is it a one-tail test or a two-tail test? So we're going to go and look at the column that corresponds to one tail, alpha equals 0.05. So for this distribution table, that's the second column of it. We're going to scroll on down to 8 degrees of freedom. So therefore, our critical t value is 1.860. And notice this is a left-tailed test, so it is to the left of 0, so it's negative 1.860. Then the next thing that we're going to do is step 3. We're going to compute the test statistic. So here is how we do that. We use the formula for a t-score. T-score and a z-score are very similar. They're always the value out of the distribution minus the mean of the distribution divided by the standard error or the standard deviation of the distribution. So here we're talking about the distribution of differences in sample values. And so we have d bar is our sample mean. Mu subscript d is the average that we're projecting, right? S subscript d, we've already computed that, and then of course we need to bring in the sample size, and so we're dividing that by the square root of n. And thankfully enough, we've gone ahead and calculated everything here. The average increase in deposits was negative 1.081, and that's in billions of dollars. In the null hypothesis, let me just scroll back up to show you, we had projected that there is no difference between deposits today versus deposits 3 years ago. So what do we put in right here for mu subscript d? We're just going to put in 0. Whatever we wrote in the null hypothesis, that's what we'll use. We have the previous value for our standard deviation, 1.937, and that is going to be divided by the square root of our sample size 9. Okay, that's pretty nice because we can pretty much do a lot of this to just clean it up so we don't have to plug in horrible things into our calculator. Let's see. So what did I do? I simplified the square root of 9 because we could do that, and then subtract 0, just throw that away, and now the rest of that we'll do with our calculator. And the calculator says we get out negative 1.674. And we will usually, whenever we are using the t-distribution, our test statistic can go all the way out to 3 digits past the decimal place, because those critical values in the t-table all go out to 3 digits past the decimal place. All right, so let's move on. So when it comes to step 4, we're going to go ahead and refer back to step 3. What decision will we make? Will we reject the null hypothesis or not reject the null hypothesis? Well, what do? This is why I always draw a picture in step 2. Not only because it helps me make sense of what it is that I'm doing, but then when we come to step 4, we've calculated our test statistic and we want to know what decision to make. Notice, where is this? It's not in this rejection region over here. We're in this zone over here, so we will not reject the null hypothesis. That's our decision. So step 4, don't reject H subscript 0. There we have it. Don't reject H subscript 0. And then in step 5, of course, summarize. So in summary, we say there's not enough evidence to show that deposits have increased over the past 3 years. All right? So this seems a little bit strange. You would say, well, okay, look, the majority of these banks, they did show an increase. There were a few that didn't show very much increase, or there were a few that even had a decrease. And so altogether, even though it looks like, for the most part, most of the deposits have increased, we can't say that this is significant enough that we can rule out sampling error and say this conclusively, or at least with more certainty. This does not pass at this particular value of alpha. If we relax this, if we said, okay, maybe we would be willing to be wrong not just 5% of the time, maybe 10% of the time, then we might be able to claim this. But as it stands right now, we're just not close enough to that cutoff point where it's now a significant increase. And we'll conclude here for this lecture. So we'll see you next time.